like I said, I'm going to have 3 little segments here. We're going to break this up into 3 parts. So it'll show up on the YouTube videos as 3 separate lectures. But they're all going to deal with the same 2-dimensional vector space. So we finally get to deal with our vector space of apples and oranges. So you have to notice carefully the difference between an A and an O in my handwriting. This is to really just emphasize the idea that we're dealing with an abstract. This could be any 2-dimensional vector space. And so I pick a basis. In this case, I'm going to call it A and O. And we're going to start out doing everything where this is 1, this is 2. So this will be our column vector 1, 0. This will be our column vector 0, 1. And we're going to define our dot product, okay, so that the dot product of an apple and orange is 0. We'll put a line through it just to distinguish between the O. And I can't write today. And they're normalized. Or in our 1, 2 notation, ij is delta ij. And so an arbitrary vector, notice in this vector space, is simply a certain number of apples plus a certain number of oranges. Right? A apples plus B oranges. And if I take a collection of apples and oranges and I add it to another collection of apples and oranges, I get apples and oranges. So I'm still a vector. If I allow for negative apples and negative oranges, I have my additive inverse. And if I have no apples or oranges, I have 0. So the only slightly strange thing is the concept of the negative apple and the negative orange. So you have to keep that in mind. Maybe that's what all that dark matter is. Now, let's consider the operator. This is a very magical operator. What it's going to do is take 1 apple and turn it into an orange. And it will turn into 1 orange. And 1 orange and turn it into 1 apple. How would you write that operator in our basis? So we want to represent our operator. We're going to call it P. We're going to call this operator P as a matrix, recalling that apples are 1, 0, and oranges are 0, 1. Anyone have a guess as how we might go? 0, 1, 1, 0 is probably what we're going to get. If we want to do this carefully, we realize that we're solving the following 2 matrix equations. Whoops. So this one gives us A equals 0 and C equals 1. And this one gives us B equals 1 and D equals 0, which is immediately what we had as our guess. So notice if it was a more complicated operator that did something not as obvious, we could solve those. Again, the other thing that happens is the first column becomes whatever we describe the action on the first vector to be, the second column the second. If it was 3 by 3, the third column the third. So there's lots of ways to think about doing this. One thing you have to get used to, because it becomes very powerful in quantum mechanics, is doing this in bracket notation. So what do I mean by that? Well, we know that the operator A gives O, and the operator on O gives A. So we will refer to the matrix elements. And this is a phrase you'll hear a lot in quantum mechanics. And the matrix elements are basically IPJ. And that's exactly, if we were then to convert it into a matrix like we're used to, the Pij are rows and columns, okay? And that tells us how to compute it in more complicated cases. Now this case is fairly straightforward. So PAA is APA. So what does that matrix element become? What is P acting on A? O. And then what is A dotted into O? 0. So notice PAA is 0, which is what we expected, right? That's the top element. So I want you to quickly work out for yourself PAO, POA, and POO. Just for practice, take a few minutes and do that. So I'll start writing them up here, and we'll see if these match what you did. How'd you do? Everyone did well? Yeah. Now notice this is a pretty simple example in some respects, but no matter how complicated it looks beyond this when you get to quantum mechanics, this is all we're doing. And if you need to do it out step by step, carefully brute force, do it. It might be a 4 by 4 matrix with 4 basis vectors, but it's still doable. And as you get more proficient in Mathematica, you can even just program Mathematica to do it for you once you have the set of rules. The one thing that's then becomes kind of powerful in useful notation is we'll write the matrix in that form, okay, as some constants, Pij, times I and j as brackets in the reverse way. And we'll have a sum over I and j. Why does this work? Well, notice now this kind of automatically, it looks redundant, but it's actually a very useful construct for later on. Notice if you want the ith j element, what I do is I multiply on the left by I and the right by j, and I times I is 1, and j times j is 1, and I get out Pij. So it's not useful for computing Pij. For computing Pij, we had to use the definition up above. But once I know the Pij's, and I want to act on any other vector, because a vector v is going to be a sum, right, over k of a sub k, k. And now, for instance, I can tell you what p times v is. It's the sum over everything, Pij I j a sub k, k, which I'm going to drop my sum because I got my repeated indices, which is Pij ak I j k. But what's jk? No. No. Remember, I'm being summing over j and k. If I have an orthonormal basis, what is the scalar product of j and k? What's the other way I can write it? I wrote it at the very beginning when I defined things. Not I. Well, the identity matrix, but I write the identity matrix in component notation as what? Delta, well, except that's not an I and a J. Delta JK. So Pij AK, whoops, I, and this became delta JK, which I now then can switch. And delta IK tells me I can set, I'm sorry, JK, my bad. Delta JK tells me I can set K equal to J, and so I have Pi, J, AJ, I. And notice this is nothing more or less than vector notation. And I just have, actually no, I have it summed out because those are, this is summed. And so if I pull out just this piece, that's the ith component of PV. And this is PV as a new vector. Because to sum over the basis vectors is how I define a vector. Now, you're probably sitting there going, wow, that was super confusing. That was the longest, hardest way I've ever seen to multiply a matrix and a vector. But imagine now you're dealing with a very abstract situation in quantum mechanics. Maybe you're even dealing with an infinite vector space where these are all represented by functions and dot products are actually integrating over the function. And you don't want to have to do all those integrals to see what you're going to get. You want to keep track of it in a compact abstract notation. So this type of notation becomes incredibly powerful as you move from a simple two-dimensional vector space to the more complicated one. So yes, doing it here, this may seem like an obscene amount of machinery to simply do that, right? And now if I wanted to do P times V, right there. I just did P times V in like 2 steps, okay? Compare that P times V to how long it took to do P times V that way. Again, seems like extra machinery and useless, but you have a chance of understanding it with the two-dimensional case. You can go in and put 1s and 2s and actually write out all these sums if you want to really see what it means and compare and see that, yes, this machinery works. And then when you're faced with that infinite dimensional vector space where it's hard to write out an infinite number of these components, you'll see that this becomes very powerful. So that's why I introduced the notation here. Yeah?
On that first line, going to the second line, how does that AK get out?
Because these are all scalars, and I can do, remember, my rule of scalar multiplication in vectors is I can move them however I want.
So J and K are on bases, right? So those are vectors?
Yeah, but if I was to think about J times some number times a vector, right, the scalar can go wherever I want in the multiplication.
All right.
Right, so all my bras and kets are vectors. They're either column or row vectors. And scalars can always move outside of all of my vector multiplication.
Wait, where did K come from? Is that what is K?
AKK is V. This. So if I come up here, this sum is V.
Thank you.
Yep. Question?
How does the AK delta JK become AJ?
Right, because the rule is I'm summing over K. The only term that's not 0 is when J equals K.
Oh.
So the only term that's left is my A sub J. And this is like the big mystery. It'll make no sense to you until it makes a lot of sense. But this step is the key to all of this index notation stuff. And it's why all the projection notation works, and it's why all this Braun-Ket notation works, is you're constantly getting delta JKs, and you're using them to change indices so you get things that you expect.
And for the delta deltas, we can, it doesn't matter what order.
Right, yeah, the j and the k doesn't matter.
It only does for the epsilon.
For the epsilons, it matters because you can get a minus sign. We good? Excellent.